Black holes are among the most mysterious objects in the universe. Their gravitational pull is so strong that nothing, not even light, can escape once it passes the event horizon. These cosmic phenomena challenge our understanding of physics, time, and the very nature of reality. Despite decades of study, black holes remain enigmas, hiding secrets that stretch the limits of human knowledge. A black hole begins its life when a massive star exhausts its nuclear fuel. Without the pressure from fusion to counteract gravity, the star collapses under its own weight. The core is compressed into an infinitely dense point called a singularity. Surrounding the singularity is the event horizon, a boundary beyond which no information or matter can escape. Crossing it means inevitable destruction. Time behaves strangely near a black hole. According to Einstein's theory of general relativity, time slows down as one approaches the event horizon. From the perspective of a distant observer, an object falling into a black hole appears to freeze, seemingly suspended at the edge. However, from the viewpoint of the falling object, time continues normally. This disparity illustrates the extreme nature of gravity near a singularity and demonstrates that black holes are not just spatial anomalies, but temporal ones as well. The event horizon is not a physical surface. It is a conceptual boundary. Anything crossing it is lost to the outside universe, yet its information poses a paradox. Quantum mechanics asserts that information cannot be destroyed, but black holes seem to contradict this rule. This contradiction is famously known as the black hole information paradox, and it has puzzled scientists for decades. Hawking radiation provides a partial answer. Stephen Hawking theorized that black holes are not completely black. They emit tiny amounts of radiation due to quantum effects near the event horizon. Over incomprehensibly long timescales, this radiation could cause black holes to evaporate completely. If true, Hawking radiation might allow some information to escape, preserving the fundamental laws of physics, but the mechanism remains deeply mysterious. Supermassive black holes, millions or billions of times the mass of our sun, lurk at the centers of most galaxies. These cosmic giants shape the evolution of galaxies, controlling star formation and influencing galactic structure. Our own Milky Way contains a supermassive black hole, Sagittarius A, with a mass of about 4 million suns. Its presence is subtle, yet its influence on surrounding stars and gas is profound. Black holes warp space and time in ways that seem impossible. Gravitational lensing occurs when light from a distant star bends around a black hole, magnifying and distorting the image. This effect allows astronomers to study objects that would otherwise be invisible, and provides indirect evidence of black holes' presence. The concept of spaghettification illustrates the extreme gravitational forces near a singularity. Imagine falling feet first into a black hole. The gravitational pull on your feet is stronger than on your head, stretching you into a long, thin shape before tearing you apart. This is not fiction. It is a real consequence of the laws of physics near extremely dense objects. Some black holes are surrounded by accretion disks, swirling masses of gas and dust heated to millions of degrees by friction. These disks emit X-rays and gamma rays, which can be observed by telescopes. By studying these emissions, scientists can determine the mass, spin, and other properties of black holes. Black holes are also potential gateways to other phenomena. Theoretical physicists propose wormholes, tunnels through space-time that could connect distant points in the universe. While purely theoretical, wormholes suggest that black holes might not only consume matter, but also link different regions of space-time in ways we have yet to comprehend. Despite all we know, black holes remain profoundly mysterious. Every discovery uncovers new questions. How does matter behave beyond the event horizon? What is the nature of singularity? Can black holes truly connect to other universes? The more we study, the more we realize that our understanding is only scratching the surface. The immense gravity of black holes affects time and space itself. In the vicinity of a black hole, tidal forces stretch space, along one axis and compress it along another, creating a warped reality. Time dilation becomes so extreme that an hour near the event horizon might equal centuries in the outside universe. Scientists have long debated whether black holes destroy information, which would violate a fundamental principle of quantum mechanics. The information paradox suggests that while matter disappears, the information it carries cannot simply vanish. Hawking proposed that black holes emit faint radiation, gradually losing mass, which might allow information to escape indirectly. The precise mechanism remains one of the greatest unsolved problems in physics. Supermassive black holes are central to galaxy formation. They anchor galaxies, regulate star formation, and influence the distribution of matter. Observations indicate that galaxies without central black holes are rare, hinting at a deep connection between cosmic structures and black hole dynamics. Spinning black holes, or Kerr black holes, introduce even more complexities. Their rotation drags space-time around them, twisting light and matter into spiral paths. Frame-dragging effects distort orbits and influence the motion of nearby objects in ways that defy intuition. The study of black holes also touches on cosmology. Dark matter and dark energy, which together make up more than 95% of the universe, are indirectly connected to black holes. Understanding how these unseen forces interact with black holes could reveal the underlying structure of the cosmos. Black holes might also be linked to the multiverse. Some theories propose that singularities could spawn entirely new universes, disconnected from our own. If true, black holes would not be destructive endpoints, but creative engines, producing new realities in ways we can scarcely imagine. The observation of black holes has advanced dramatically. In 2019, the Event Horizon Telescope captured the first direct image of a black hole, revealing a glowing ring surrounding the dark shadow. This confirmed decades of theoretical predictions while raising fresh questions about matter, energy, and the behavior of light near the event horizon. Despite technological advances, the inner workings of black holes remain largely speculative. What occurs inside the singularity, beyond the event horizon, is a mystery that may forever elude observation. Yet each discovery propels science forward, challenging physicists to rethink fundamental concepts of space, time, and reality itself. Black holes' gravitational influence extends far beyond their immediate vicinity. They warp galaxies, accelerate particles to near-light speed, and generate relativistic jets that span thousands of light years. These jets, composed of high-energy particles, are thought to originate from the interactions between the black hole's spin and its accretion disk, creating some of the most energetic phenomena in the universe. Time and space near black holes are linked in ways that defy common sense. A hypothetical traveler falling into a black hole would experience extreme stretching, compression, and temporal distortion. The path to the singularity is not just physical, but also temporal, bending the concept of cause and effect. Researchers speculate that black holes may serve as natural laboratories for quantum gravity, the yet-to-be formulated theory reconciling general relativity with quantum mechanics. Studying these extreme objects may offer insights into the unification of physics and the true nature of reality. Some theoretical models suggest that information swallowed by black holes may leave imprints on the event horizon itself. This holographic principle posits that all information about three-dimensional objects inside a black hole could be encoded on its two-dimensional surface, hinting at a deeper connection between gravity and information theory. Black holes are also central to discussions of entropy and thermodynamics. They possess entropy proportional to the area of their event horizon, not their volume, a concept that challenges classical understanding. The study of black hole thermodynamics bridges physics, information theory, and cosmology, revealing deep connections between seemingly disparate fields. Accretion disks around black holes generate extreme radiation visible across millions of light years. These energetic emissions allow astronomers to infer black hole properties indirectly, revealing rotation rates, mass, and sometimes even magnetic field strength. Black holes are not solitary objects. In binary systems, black holes interact with companion stars, drawing matter from them in spectacular displays of energy. These interactions illuminate processes that cannot be reproduced in laboratories on Earth, offering unique insights into the laws of physics. Part 4, 3001-4000 Kelvin. The mysteries of black holes extend to cosmic evolution. Supermassive black holes influence the development of galaxies, acting as anchors around which stars and gas congregate. Their presence is crucial for the formation of planetary systems and, by extension, for the potential emergence of life. Some physicists hypothesize that black holes could connect to other universes. Theoretical constructs such as Einstein-Rosen bridges, wormholes, suggest that a black hole in our universe might have an exit point elsewhere, although traversing such a bridge would likely be fatal due to tidal forces. The energy produced in the vicinity of black holes is staggering. Quasars, powered by accretion onto supermassive black holes, shine brighter than entire galaxies, emitting vast quantities of radiation across the electromagnetic spectrum. These cosmic beacons allow astronomers to probe the early universe and study black hole formation billions of years ago. Black holes also provide a unique testing ground for relativity. The extreme curvature of space-time near a singularity enables precise tests of Einstein's equations, revealing both their strengths and limitations. Observations of stellar orbits around Sagittarius A confirm predictions of general relativity with astonishing accuracy. Despite all we know, questions remain. How do black holes merge? What happens when two singularities collide? Gravitational wave astronomy has begun to answer these questions, detecting ripples in space-time caused by black hole mergers. These discoveries open a new window into understanding the universe's most violent events. The mysteries of black holes extend to cosmic evolution. Supermassive black holes influence the development of galaxies, acting as anchors around which stars and gas congregate. Their presence is crucial for the formation of planetary systems and, by extension, for the potential emergence of life. Some physicists hypothesize that black holes could connect to other universes. Theoretical constructs such as Einstein-Rosen bridges, wormholes, suggest that a black hole in our universe might have an exit point elsewhere, although traversing such a bridge would likely be fatal due to tidal forces. The energy produced in the vicinity of black holes is staggering. Quasars, powered by accretion onto supermassive black holes, shine brighter than entire galaxies, emitting vast quantities of radiation across the electromagnetic spectrum. These cosmic beacons allow astronomers to probe the early universe and study black hole formation billions of years ago. Black holes also provide a unique testing ground for relativity. The extreme curvature of space-time near a singularity enables precise tests of Einstein's equations, revealing both their strengths and limitations. Observations of stellar orbits around Sagittarius A confirm predictions of general relativity with astonishing accuracy. Despite all we know, questions remain. How do black holes merge? What happens when two singularities collide? Gravitational wave astronomy has begun to answer these questions, detecting ripples in space-time caused by black hole mergers. These discoveries open a new window into understanding the universe's most violent events. Kerr black holes, or spinning black holes, twist space-time around them, creating complex patterns of motion. Frame-dragging effects influence nearby objects, altering their orbits in ways that are still being studied. These phenomena challenge our intuition and demonstrate that space-time is a dynamic, malleable fabric. Black holes are intimately connected to the fate of the universe. Their growth, mergers, and interactions influence cosmic evolution on a grand scale. Understanding these processes is critical for constructing accurate models of galaxy formation and evolution. The interior of a black hole remains the ultimate unknown. Physics as we know it breaks down at the singularity, leaving questions that may never be answered. Speculation ranges from connections to other universes to exotic states of matter that defy conventional understanding. Observing black holes indirectly through radiation, gravitational effects, and stellar motions has transformed astronomy. Each discovery provides new insights, yet simultaneously deepens the mystery. Black holes challenge scientists to think beyond ordinary physics, inspiring new theories and technologies. Ultimately, black holes remind us of the limits of human knowledge. They are both destructive and creative, shaping galaxies, bending time, and challenging the very notion of reality. Each discovery raises deeper questions about the universe. Are black holes truly the end of matter, or are they portals to something unimaginable? Could they connect to other dimensions or even other universes? The dark truth of black holes is that they are gateways to the unknown, revealing both the fragility of our understanding and the infinite complexity of the cosmos. Exploring them is not just a scientific pursuit, it is a journey into the deepest mysteries of existence itself. Black holes teach us humility. They show that even the most brilliant human minds can only scratch the surface of reality. And as we continue to study them, we are reminded that the universe is far stranger, darker, and more wondrous than we can ever imagine.